5. The Stone Breakers. At just the time that Henry Cavendish was completing his experiments in London, 400 miles away in Edinburgh, another kind of concluding moment was about to take place with the death of James Hutton. This was bad news for Hutton, of course, but good news for science as it cleared the way for a man named John Playfair to rewrite Hutton's work without fear of embarrassment. Hutton was by all accounts a man of the keenest insights and liveliest conversation, a delight in company, and without rival when it came to understanding the mysterious slow processes that shape the earth. Unfortunately, it was beyond him to set down his notions in a form that anyone could begin to understand. He was, as one biographer observed with an all but audible sigh, almost entirely innocent of rhetorical accomplishments. Nearly every line he penned was an invitation to slumber. Here he is in his 1795 masterwork, a theory of the earth with proofs and illustrations, discussing, well, something. The world which we inhabit is composed of the materials, not of the earth, which was the immediate predecessor of the present, but of the earth which, in ascending from the present, we consider as the third, and which had preceded the land that was above the surface of the sea, while our present land was yet beneath the water of the ocean. Yet almost single-handedly and quite brilliantly, he created the science of geology and transformed our understanding of the earth. Hutton was born in 1726 into a prosperous Scottish family and enjoyed the sort of material comfort that allowed him to pass much of his life in a genially expansive round of light work and intellectual betterment. He studied medicine, but found it not to his liking, and turned instead to farming, which he followed in a relaxed and scientific way on the family estate in Berwickshire. Tiring of field and flock, in 1768 he moved to Edinburgh, where he founded a successful business producing sal ammoniac from coal soot, and busied himself with various scientific pursuits. Edinburgh at that time was a center of intellectual vigor, and Hutton luxuriated in its enriching possibilities. He became a leading member of a society called the Oyster Club, where he passed his evenings in the company of men such as the economist Adam Smith, the chemist Joseph Black, and the philosopher David Hume, as well as such occasional visiting sparks as Benjamin Franklin and James Watt. In the tradition of the day, Hutton took an interest in nearly everything from mineralogy to metaphysics. He conducted experiments with chemicals, investigated methods of coal mining and canal building, toured salt mines, speculated on the mechanisms of heredity, collected fossils, and propounded theories on rain, the composition of air, and the laws of motion, among much else. But his particular interest was geology. Among the questions that attracted interest in that fanatically inquisitive age was one that had puzzled people for a very long time, namely, why ancient clam shells and other marine fossils were so often found on mountain tops. How on earth did they get there? Those who thought they had a solution fell into two opposing camps. One group, known as the Neptunists, were convinced that everything on Earth, including seashells in improbably lofty places, could be explained by rising and falling sea levels. They believed that mountains, hills, and other features were as old as the Earth itself and were changed only when water sloshed over them during periods of global flooding. Opposing them were the Plutonists, who noted that volcanoes and earthquakes, among other enlivening agents, continually changed the face of the planet, but clearly owed nothing to wayward seas. The Plutonists also raised awkward questions about where all the water went when it wasn't in flood. If there was enough of it at times to cover the Alps, then where, pray, was it during times of tranquility such as now? Their belief was that the earth was subject to profound internal forces as well as surface ones. However, they couldn't convincingly explain how all those clamshells got up there. It was while puzzling over these matters that Hutton had a series of exceptional insights. From looking at his own farmland, he could see that soil was created by the erosion of rocks and that particles of the soil were continually washed away and carried off by streams and rivers and redeposited elsewhere. He realized that if such a process were carried to its natural conclusion, then the earth would eventually be worn quite smooth. Yet everywhere around him there were hills. Clearly there had to be some additional process, some form of renewal and uplift that created new hills and mountains to keep the cycle going. The marine fossils on mountain tops, he decided, had not been deposited during floods, but had risen along with the mountains themselves. He also deduced that it was heat within the earth that created new rocks and continents and thrust up mountain chains. It is not too much to say that geologists wouldn't grasp the full implications of this thought until 200 years later, when finally they adopted the concept of plate tectonics. Above all, what Hutton's theory suggested was that the processes that shaped the earth required huge amounts of time, far more than anyone had ever dreamt. There were enough insights here to transform utterly our understanding of the planet. In 1785, Hutton worked his ideas up into a long paper, which was read at consecutive meetings of the Royal Society of Edinburgh. It attracted almost no notice at all. It's not hard to see why. Here, in part, is how he presented it to his audience. In the one case, the forming cause is in the body which is separated, for after the body has been actuated by heat, it is by the reaction of the proper matter of the body that the chasm which constitutes the vein is formed. In the other case, again, the cause is extrinsic in relation to the body in which the chasm is formed. There has been the most violent fracture and divulsion, but the cause is still too sick, and it appears not in the vein, for it is not every fracture and dislocation of the solid body of our earth in which minerals or the proper substances of mineral veins are found. Needless to say, almost no one in the audience had the faintest idea what he was talking about. Encouraged by his friends to expand his theory, in the touching hope that he might somehow stumble onto clarity in a more expansive format, Hutton spent the next 10 years preparing his magnum opus, which was published in 2 volumes in 1795. Together, the two books ran to nearly 1,000 pages and were remarkably worse than even his most pessimistic friends had feared. Apart from anything else, nearly half the completed work now consisted of quotations from French sources still in the original French. A third volume was so unenticing that it wasn't published until 1899, more than a century after Hutton's death, and the fourth and concluding volume was never published at all. Hutton's theory of the Earth is a strong candidate for the least read important book in science, or at least it would be if there weren't so many others. Even Charles Lyell, the greatest geologist of the following century, and a man who read everything, admitted he couldn't get through it. Luckily, Hutton had a Boswell in the form of John Playfair, a professor of mathematics at the University of Edinburgh and a close friend, who not only could write silken prose but, thanks to many years at Hutton's elbow, actually understood what Hutton was trying to say most of the time. In 1802, 5 years after Hutton's death, Playfair produced a simplified exposition of the Huttonian principles entitled Illustrations of the Huttonian Theory of the Earth. The book was gratefully received by those who took an active interest in geology, which in 1802 was not a large number. That, however, was about to change, and how. In the winter of 1807, 13 like-minded souls in London got together at the Freemasons' Tavern at Long Acre, in Covent Garden, to form a dining club to be called the Geological Society. The idea was to meet at once a month to swap geological notions over a glass or two of Madeira and a convivial dinner. The price of the meal was set at a deliberately hefty 15 shillings to discourage those whose qualifications were merely cerebral. It soon became apparent, however, that there was a demand for something more properly institutional, with a permanent headquarters where people could gather to share and discuss new findings. In barely a decade, membership grew to 400, still all gentlemen, of course, and the geological was threatening to eclipse the Lyell as the premier scientific society in the country. The members met twice a month from November until June, when virtually all of them went off to spend the summer doing field work. These weren't people with a pecuniary interest in minerals, you understand, or even academics for the most part, but simply gentlemen with the wealth and time to indulge a hobby at a more or less professional level. By 1830, there were 745 of them, and the world would never see the like again. It is hard to imagine now, but geology excited the 19th century, positively gripped it in a way that no science ever had before or would again. In 1839, when Roderick Murchison published The Silurian System, a plump and ponderous study of a type of rock called greywacke, it was an instant bestseller, racing through 4 editions, even though it cost 8 guineas a copy and was, in true Huttonian style, unreadable. As even a Murchison supporter conceded, it had a total want of literary attractiveness, and when, in 1841, the great Charles Lyell traveled to America to give a series of lectures in Boston, sell-out audiences of 3,000 at a time packed into the Lowell Institute to hear his tranquilizing descriptions of marine zeolites and seismic perturbation in Campania. Throughout the modern thinking world, but especially in Britain, men of learning ventured into the countryside to do a little stone breaking, as they called it. It was a pursuit taken seriously, and they tended to dress with appropriate gravity in top hats and dark suits, except for the Reverend William Buckland of Oxford, whose habit it was to do his fieldwork in an academic gown. The field attracted many extraordinary figures, not least the aforementioned Murchison, who spent the first 30 or so years of his life galloping after foxes, converting aeronautically challenged birds into puffs of drifting feathers, with buckshot, and showing no mental agility whatever beyond the needed to read the Times, or play a hand of cards. Then he discovered an interest in rocks and became, with rather astounding swiftness, a titan of geological thinking. Then there was Dr. James Parkinson, who was also an early socialist and author of many provocative pamphlets with titles like Revolution Without Bloodshed. In 1794, he was implicated in a faintly lunatic sounding conspiracy called the Pope Gun Plot, in which it was planned to shoot King George III in the neck with a poisoned dart as he sat in his box at the theater. Parkinson was hauled before the Privy Council for questioning and came within an ace of being dispatched in irons to Australia before the charges against him were quietly dropped. Adopting a more conservative approach to life, he developed an interest in geology and became one of the founding members of the Geological Society and the author of an important geological text, Organic Remains of a Former World, which remained in print for half a century. He never caused trouble again. Today, however, we remember him for his landmark study of the affliction then called the shaking palsy, but known ever since as Parkinson's disease. Parkinson had one other slight claim to fame. In 1785, he became possibly the only person in history to win a natural history museum in a raffle. The museum, in London's Leicester Square, had been founded by Sir Ashton Lever, who had driven himself bankrupt with his unrestrained collecting of natural wonders. Parkinson kept the museum until 1805, when he could no longer support it and the collection was broken up and sold. Not quite as remarkable in character but more influential than all the others combined was Charles Lyell. Lyell was born in the year that Hutton died and only 70 miles away in the village of Kinnordy. Though Scottish by birth, he grew up in the far south of England, in the New Forest of Hampshire, because his mother was convinced that Scots were feckless drunks, as was generally the pattern with 19th century gentlemen scientists. Lyell came from a background of comfortable wealth and intellectual vigor. His father, also named Charles, had the unusual distinction of being a leading authority on the poet Dante and on Moses. Orthorhynchium Lyelli, which most visitors to the English countryside will at some time have sat on, is named for him. From his father, Lyell gained an interest in natural history. But it was at Oxford, where he fell under the spell of the Reverend William Buckland, he of the flowing gowns, that the young Lyell began his lifelong devotion to geology. Buckland was a bit of a charming oddity. He had some real achievements, but he is remembered at least as much for his eccentricities. He was particularly noted for a menagerie of wild animals, some large and dangerous, that were allowed to wander through his house and garden, and for his desire to eat his way through every animal in creation, depending on whim and availability. Guests to Buckland's house might be served baked guinea pig, mice in batter, roasted hedgehog, or boiled Southeast Asian sea slug. Buckland was able to find merit in them all, except the common garden mole, which he declared disgusting. Almost inevitably, he became the leading authority on coprolites, fossilized faces, and had a table made entirely out of his collection of specimens. Even when conducting serious science, his manner was generally singular. Once Mrs. Buckland found herself being shaken awake in the middle of the night, her husband crying in excitement, "My dear, I believe that Kerotherium's footsteps are undoubtedly testudinal." Together they hurried to the kitchen in their night clothes. Mrs. Buckland made a flour paste, which she spread across the table, while the Reverend Buckland fetched the family tortoise. Plunking it onto the paste, they goaded it forward and discovered to their delight that its footprints did indeed match those of the fossil Buckland had been studying. Charles Darwin thought Buckland's a buffoon. That was the word he used. That was the word he used. But Lyell appeared to find him inspiring and liked him well enough to go touring with him in Scotland in 1824. It was soon after this trip that Lyell decided to abandon a career in law and devote himself to geology full time. Lyell was extremely short-sighted and went through most of his life with a painted squint, which gave him a troubled air. Eventually he would lose his sight altogether. His other slight peculiarity was the habit, when distracted by thought, of taking up improbable positions on furniture, lying across two chairs at once or resting his head on the seat of a chair while standing up. To quote his friend Darwin, often when lost in thought he would sling so low in a chair that his buttocks would all but touch the floor. Lyell's only real job in life was a professor of geology at King's College in London from 1831 to 1833. It was just at this time that he produced the Principles of Geology, published in 3 volumes between 1830 and 1833, which in many ways consolidated and elaborated upon the thoughts first voiced by Hutton a generation earlier. Although Lyell never read Hutton in the original, he was a keen student of Playfair's reworked version. Between Hutton's day and Lyell's, there rose a new geological controversy, which largely superseded, but is often confused with, the old Neptunian-Plutonian dispute. The new battle became an argument between catastrophism and uniformitarianism, unattractive terms for an important and very long-running dispute. Catastrophists, as you might expect from the name, believe that the earth was shaped by abrupt cataclysmic events, floods principally, which is why catastrophism and Neptunism are often wrongly bundled together. Catastrophism was particularly comforting to clerics like Buckland because it allowed them to incorporate the biblical flood of Noah into serious scientific discussions. Uniformitarians, by contrast, believed that changes on Earth were gradual and that nearly all Earth processes happened slowly over immense spans of time. Hutton was much more the father of the notion than Lyell, but it was Lyell most people read, and so he became in most people's minds then and now the father of modern geological thought. Lyell believed that the Earth's shifts were uniform and steady, that everything that had ever happened in the past could be explained by events still going on today. Lyell and his adherents didn't just disdain catastrophism, they detested it. Catastrophists believed that extinction were part of a series in which animals were repeatedly wiped out and replaced with new sets, a belief that the naturalist T. H. Huxley mockingly likened to a succession of rubbers of whist, at the end of which the players upset the table and called for a new pack. It was too convenient a way to explain the unknown. Never was there a dogma more calculated to foster indolence and to blunt the keen edge of curiosity, sniffed Lyell. Lyell's oversights were not inconsiderable. He failed to explain convincingly how mountain ranges were formed and overlooked glaciers as an agent of change. He refused to accept Agassiz's idea of ice ages, the refrigeration of the globe, as he dismissively termed it, and was confident that mammals would be found in the oldest fossiliferous beds. He rejected the notion that animals and plants suffered sudden annihilations, and believed that all the principal animal groups, mammals, reptiles, fish, and so on, had coexisted since the dawn of time. On all of these he would ultimately be proved wrong. Yet it would be nearly impossible to overstate Lyell's influence. The Principle of Geology went through 12 editions in his lifetime and contained notions that shaped geological thinking far into the 20th century. Darwin took a first edition with him on the Beagle voyage and wrote afterwards that the great merit of the principles was that it altered the whole tone of one's mind, and therefore that when seeing a thing never seen by Lyell, one yet saw it partially through his eyes. In short, He thought him nearly a god, as did many of his generation. It is a testament to the strength of Lyell's sway that in the 1980s, when geologists had to abandon just a part of his theory to accommodate the impact theory of extinctions, it nearly killed them. But that is another chapter. Meanwhile, geology had a great deal of sorting out to do, and not all of it went smoothly. From the outset, geologists tried to categorize rocks by the periods in which they were laid down, but there were often bitter disagreements about where to put the dividing lines, none more so than a long, running debate that became known as the Great Devonian Controversy. The issue arose when the Reverend Adam Sedgwick of Cambridge claimed that for the Cambrian period a layer of rock that Roderick Murchison believed belonged rightly to the Silurian. The dispute raged for years and grew extremely heated. "De la Beche is a dirty dog," Murchison wrote to a friend in a typical outburst. Some sense of the strength of feeling can be gained by glancing through the chapter titles of Martin J. S. Rudwick's excellent and somber account of the issue, The Great Devonian Controversy. These begin innocuously enough with headings such as "Arenas of Gentlemanly Debate" and "Unraveling the Greywacke," but then proceed on to "The Greywacke Defended and Attacked," reproofs and recriminations, the spread of ugly rumors. Weber reckons his heresy, putting a provincial in his place, and, in case there was any doubt that this was war, Murchison opens the Rhineland campaign. The fight was finally settled in 1879 with the simple expedient of coming up with a new period, the Ordovician, to be inserted between the Cambrian and Silurian. Because the British were the most active in the early years of the discipline, British names are predominant in the geological lexicon. Devonian is of course from the English county of Devon. Cambrian comes from the Roman name for Wales, while Ordovician and Silurian recall ancient Welsh tribes, the Ordovices and Siluris. But with the rise of geological prospecting elsewhere, names began to creep in from all over, Jurassic rivers to the Jura Mountains on the border of France and Switzerland. Permian recalls the former Russian province of Perm in the Ural Mountains. For Cretaceous, from the Latin for chalk, we are indebted to a Belgian geologist with the perky name of J. J. Domalius Dalloy. Originally, geological history was divided into four spans of time: primary, secondary, tertiary, and quaternary. The system was too neat to last, and soon geologists were contributing additional divisions while eliminating others. Primary and secondary fell out of use altogether, while quaternary was discarded by some but kept by others. Today only tertiary remains as a common designation everywhere, even though it no longer represents a third period of anything. Lyell, in his Principles, introduced additional units known as epochs, or series to cover the period since the age of dinosaurs, among them Pleistocene, most recent, Pliocene or more recent, Miocene, moderately recent, and rather endearingly vague Oligocene, but a little recent. Lyell originally intended to employ synchronous for his endings, giving us such crunchy designations as Meiosynchronous and Pleiosynchronous. The Reverend William Whewell, an influential man, objected on etymological grounds and suggested instead an "ius" pattern, producing Meionius, Pleionius, and so on. The "-cene" terminations were something of a compromise. Nowadays, and speaking very generally, geological time is divided first into four great chunks known as eras. Precambrian, Paleozoic from the Greek meaning old life, Mesozoic middle life, and Cenozoic recent life. These four eras are further divided into anywhere from a dozen to 20 subgroups, usually called periods, though sometimes known as systems. Most of these are also reasonably well known: Cretaceous, Jurassic, Triassic, Silurian, and so on. Then come Lyell's epochs, the Pleistocene, Miocene, and so on, which apply only to the most recent but paleontologically busy 65 million years. And finally, we have a mess of finer subdivisions known as stages or ages. Most of these are named nearly always awkwardly after places: Illinoisan, Desmoinasian, Croatian, Chimeridgian, and so on, like vein. Altogether, according to John McPhee, these number in the tens of dozens. Fortunately, unless you take up geology as a career, you are unlikely ever to hear any of them again. Further confusing the matter is that the stages or ages in North America have different names from the stages in Europe and often only roughly intersect with them in time. Thus, the North American Cincinnatian stage mostly corresponds with the Ashgilian stage in Europe, plus a tiny bit of slightly earlier Caradocian stage. Also, all this changes from textbook to textbook and from person to person, so that some authorities describe 7 recent epochs, while others are content with 4. In some books, too, you will find the tertiary and quaternary taken out and replaced by periods of different lengths called the Paleogene and Neogene. Others divide the Precambrian into 2 eras: the very ancient Archean and the more recent Proterozoic. Sometimes, too, you will see the term Phanerozoic used to describe the span encompassing the Cenozoic, Mesozoic, and Paleozoic eras. Moreover, all this applies only to units of time. Rocks are divided into quite separate units known as systems, series, and stages. A distinction is also made between late and early, referring to time, and upper and lower, referring to layers of rock. It can all get terribly confusing to non-specialists, but to a geologist these can be matters of passion. I have seen grown men glow incandescent with rage over this metaphorical millisecond in life's history. The British paleontologist Richard Fortey has written with regard to a long-running 20th century dispute over where the boundary lies between the Cambrian and Ordovician. At least, today we can bring some sophisticated dating techniques to the table. For most of the 19th century, geologists could draw on nothing more than the most hopeful guesswork. The frustrating position then was that although they could place the various rocks and fossils in order by age, they had no idea how long any of those ages was. When Buckland speculated on the antiquity of an Ichthyosaurus skeleton, he could do no better than suggest that it had lived somewhere between 10,000 and more than 10,000 times 10,000 years earlier. Although there was no reliable way of dating periods, there was no shortage of people willing to try. The most well-known early attempt was made in 1650 when Archbishop James Ussher of the Church of Ireland made a careful study of the Bible and other historical sources and concluded in a hefty tome called Annals of the Old Testament that the earth had been created at midday on 23rd October 4004 BC, an assertion that has amused historians and textbook writers ever since. There is a persistent myth, incidentally, and one propounded in many serious books that Usher's views dominated scientific beliefs well into the 19th century and that it was Lyell who put everyone straight. Stephen Jay Gould in Times Arrow cites as a typical example this sentence from a popular book of the 1980s. Until Yale published this book, most thinking people accepted the idea that the Earth was young. In fact, no, as Martin J. S. Rudwick puts it, no geologist of any nationality whose work was taken seriously by other geologists advocated a timescale confined within the limits of a literalistic exegesis of Genesis. Even the Reverend Buckland, as pious as a soul as the 19th century produced, noted that nowhere did the Bible suggest that God made heaven and earth on the first day, but merely in the beginning. That beginning, he reasoned, may have lasted millions upon millions of years. Everyone agreed that the earth was ancient. The question was simply, how ancient? One of the better early ideas at dating the planet came from the ever-reliable Edmond Halley, who in 1715 suggested that if you divided the total amount of salt in the world's seas by the amount added each year, you would get the number of years that the oceans had been in existence, which would give you a rough idea of Earth's age. The logic was appealing, but unfortunately no one knew how much salt was in the sea or by how much it increased each year, which rendered the experiment impracticable. The first attempt at measurement that could be called remotely scientific was made by the Frenchman Georges-Louis Leclerc, Comte de Buffon, in the 1770s. It had long been known that the Earth radiated appreciable amounts of heat. That was apparent to anyone who went down a coal mine, but there wasn't any way of estimating the rate of dissipation. Buffon's experiment consisted of heating spheres until they glowed white hot, and then estimating the rate of heat loss by touching them, presumably very lightly at first, as they cooled. From this, he guessed the Earth's age to be somewhere between 75,000 and 168,000 years old. This was of course a wild underestimate, but it was a radical notion nonetheless, and Buffon found himself threatened with excommunication for expressing it. A practical man, he apologized at once for his thoughtless heresy, then cheerfully repeated the assertion throughout his subsequent writings. By the middle of the 19th century, most learned people thought the Earth was at least a few million years old, perhaps even some tens of millions years old, but probably not more than that. So it came as a surprise when in 1859, in On the Origin of Species, Charles Darwin announced that the geological processes that created the world an area of southern England stretching across Kent, Surrey, and Sussex had taken, by his calculations, 306,662,400 years to complete. The assertion was remarkable partly for being so arrestingly specific but even more for flying in the face of accepted wisdom about the age of the earth. It proved so contentious that Darwin withdrew it from the third edition of the book. The problem at its heart remained, however. Darwin and his geological friends needed the earth to be old, but no one could come up with a way to make it so. Unfortunately for Darwin and for progress, the question came to the attention of the great Lord Kelvin, who, though indubitably great, was then still just plain William Thomson. He wouldn't be elevated to the peerage until 1892, when he was 68 years old and nearing the end of his career, but I shall follow the convention here of using the name retroactively. Kelvin was one of the most extraordinary figures of the 19th century. Indeed, of any century, the German scientist Hermann von Helmholtz, no intellectual slouch himself, wrote that Kelvin had by far the greatest intelligence and lucidity and mobility of thought of any man he had ever met. I felt quite wooden beside him sometimes, he added, a bit dejectedly. The sentiment is understandable, for Kelvin really was a kind of Victorian Superman. He was born in 1824 in Belfast, the son of a professor of mathematics at the Royal Academical Institution, who soon afterwards transferred to Glasgow. There, Kelvin proved himself such a prodigy that he was admitted to Glasgow University at the exceedingly tender age of 10. By the time he had reached his early twenties. He had studied at institutions in London and Paris, graduated from Cambridge, where he won the university's top prizes for rowing and mathematics, and somehow found time to launch a musical society as well, been elected a Fellow of Peterhouse, and written in French and English a dozen papers in pure and applied mathematics of such dazzling originality that he had to publish them anonymously for fear of embarrassing his superiors. At the age of 22, he returned to Glasgow to take up a professorship in natural philosophy, a position he would hold for the next 53 years. In the course of a long career, he lived to 1907 and the age of 83. He wrote 661 papers, accumulated 69 patents from which he grew abundantly wealthy and gained renown in nearly every branch of the physical sciences. Among much else, he suggested the method that led directly to the invention of refrigeration, devised the scale of absolute temperature that still bears his name, invented the boosting devices that allowed telegrams to be sent across oceans, and made innumerable improvements to shipping and navigation. From the invention and made innumerable improvements to shipping and navigation, from the invention of a popular marine compass to the creation of the first depth sounder, and those were merely his practical achievements. His theoretical work in electromagnetism, thermodynamics, and the wave theory of light was equally revolutionary. He had really only one flaw that was an inability to calculate the correct age of the Earth. The question occupied much of the second half of his career, but he never came anywhere near getting it right. His first effort in 1862 for an article in a popular magazine called Macmillan's suggested that the Earth was 98 million years old, but cautiously allowed that the figure could be as low as 20 million years or as high as 400 million. With remarkable prudence, he acknowledged that his calculation could be wrong if sources now unknown to us are prepared in the great storehouse of creation. But it was clear that he thought that unlikely. With the passage of time, Calvin would become more forthright in his assertions and less correct. He continually revised his estimates downwards from a maximum of 400 million years to 100 million years, then to 50 million years, and finally in 1897 to a mere 24 million years. Kelvin wasn't being willful. It was simply that there was nothing in physics that could explain how a body the size of the sun could burn continuously for more than a few tens of millions of years at most without exhausting its fuel. Therefore, it followed that the sun and its planets were relatively but inescapably youthful. The problem was that nearly all the fossil evidence contradicted this, and suddenly in the 19th century there was a lot of fossil evidence.